The dot product satisfies several formal properties that you should be familiar with and that often make calculations much easier. So in the following list of 5 items, u and v and w are vectors and c is a scalar. So first, if you take the dot product of u and v, it's going to give you the same scalar as taking the dot product of v and u. This should be clear from the definition of dot product. The second property is also very straightforward to check. U dot v plus w is the same thing as u dot v plus u dot w. And property 3, a scalar times u dot v can be distributed as the scalar times u, then dotted with v, or u dot the scalar times v. And then the last 2 properties are that the dot product of v with itself is equal to its magnitude squared, and that the dot product of a vector with itself is always positive, and it's 0 if and only if the vector is the 0 vector. So as you're studying, you should go through these properties and make sure that they make sense. You should check some of them. And by that I mean, say if you wanted to check property number 2. You would take u to be u1 through un. You would take v to be v1 through vn, and w to be w1 through wn, and you would work out both sides of the equation. This is something you should do while you study. So on the left-hand side of the equation, I have u1 through un, dot product with v plus w. So in parentheses, I would have the vector v added to the vector w. And here I need to carefully apply my definitions. When you add 2 vectors together, you add them component-wise. So inside this parentheses, I would add the components of v and w, giving me the new vector v1 plus w1, with the last entry vn plus wn. And this gets dot producted with u1 through un. At this stage, I would use the definition of the dot product and see that this gives me u1 times v1 plus w1 added to the next summand and so on. And the last summand is un times vn plus wn. Now, I'm not going to continue with this checking, but you would distribute the u into each one of these parentheses and see that you really get the same thing as what's on the right-hand side of the equation. So I encourage you to go through and check these formal properties. One thing we do need to discuss further, though, is property number 4, because this deals with the norm, or the length, or also known as the magnitude of the vector v. So let's discuss a little bit the definition of the length of a vector. This is also called the norm of the vector or the magnitude of the vector v in Rn. So by definition, the length of v is, when v is v1 through vn, the square root of the first entry v1 squared plus the second entry v2 squared, all the entries squared and added up under the radical. This is a typical distance-looking equation in Euclidean space. And let me point out that in 2D you can think of this as nothing more than your usual Pythagorean theorem. So let me sketch what I mean. So let me put a point v1, v2. in R2. Well, basic Euclidean geometry tells me that if I take this point and I draw a line straight down to the axis, it's going to form a 90-degree angle. So I have a right angle triangle, the sides of which are length v1 and v2. Now the Pythagorean theorem tells me that v1 squared plus v2 squared is going to give me the hypotenuse squared. And if I want the length of that hypotenuse, I can take the square root of v1 squared plus v2 squared. And that gives me the length of the hypotenuse. And that's what I see in this formula. Okay, so this is your typical Euclidean distance. And I want to observe something else about this formula. And that's that if I take the dot product of the vector v with itself, that dot product is this length squared. So let's do a little quickie example. Let's take the example of the vector v equals 1, 2, 3, and let's calculate its norm. So we can take v dot v. This is 1, 2, 3 dotted with itself. So of course this is going to be 1 squared plus 2 squared plus 3 squared, which works out to be 14. So the norm of v squared is 14, and the norm of v is the square root of 14. And let me mention another fact. This is a useful one. You can always scale. So I mean scale up or scale down a vector. And it better be a non-zero vector, so any vector other than the zero vector, so that it has length 1. A vector that has length 1 is called a unit vector. So let's see how to do this. If v is not the zero vector, then your unit vector in the direction of v is v divided by the length of v. Okay, this is called the unit vector in the same direction as v. And it's called that because, well, if you plot them, they're going to be pointed in the same direction. So let's unpack that statement. We want to understand exactly why you can take any vector v and upon dividing by its own length, get a vector that has length 1 that's pointed in the same direction. All right, first of all, it's pointed in the same direction because you're just scaling it. You're scaling it out or you're scaling it back, so it doesn't change the direction. But why does it have length 1? Well, let's look at the formulation. When we take v and we divide by the norm of v, what you're really doing is scalar multiplying. The scalar is 1 over the norm of v. This quantity is a number, this is the scalar, and it's being multiplied times the vector v, giving you a new vector. The way scalar multiplication works is it multiplies times every entry inside the vector. So you see 1 over the length of v appearing in the first entry, in the second entry, in the third entry, and so on. So this is what v divided by the length of v looks like. So let's calculate the length of this new vector by applying the length formula. We're now going to look at the length of v divided by its own norm. Just by following the formula, we see that this ought to be the square root of the first entry, which comes from here, squared, plus the second entry squared, and so on and so forth, all inside the square root. And then use a little bit of algebra to rewrite things. Every single entry has a 1 over the length of v being squared, so you can pull that out of the sum of v1 squared plus v2 squared, and out through vn squared. Then because this is a square under the square root, you can move it to the outside as a 1 over the length of v, leaving the square root of v1 squared plus v2 squared out through vn squared inside the radical. But this term is again the length of v, so you end up with the length of v over the length of v, which is 1.